Hi everyone, today I'll talk about my IW project, which is on training robust RL agents. So the motivation of this project basically comes from the fact that an agent can discover unsupervised skills without a task-related reward function. And this process of learning diverse and reusable pre-trained skills are actually very useful to serve as initial parameters before we train for some specific downstream tasks. And this is essential in settings where the robustness of the agent skills are very important. But there are still some challenges in this approach. One of the challenges is that to handle continuous and high dimensional state spaces, it is very computationally expensive and it is also very unstable in training. The goal of my project is basically to explore new methods that can either improve the current process of learning pre-trained skills or make some adjustment to the current methods so that it can lead to better results on downstream tasks. There are many potential applications for unsupervised skill discovery. For example, in robotics, autonomous robots in dynamic environments such as warehouses need to navigate the environment. So it's important to have a diverse set of skills. And it also has some applications in gaming. And here are some of the work that's related to my research project. So the DIAYM paper basically introduced a method for unsupervised skill discovery by using mutual information to encourage diverse behavior of the agent. The skills are encoded as latent variables, and what the agent is trying to do is that after it observes an outcome from a skill, it tries to predict the skill based on the outcome. And it turns out using this method, it can learn a different set of skills that produce distinguishable outcomes. One of the challenges of this approach is that it sometimes fails to explore the environment due to a lack of incentives. And the second paper, Metra, that I looked at, basically tries to make RL scalable by focusing on a latent space that basically has a mapping to the state space. And by learning a diverse set of behavior on the latent space, it can also approximately covers the state space. This is scalable to high dimensional environment and turns out it does better on downstream tasks than previous method. And finally, I looked at the paper on contrastive successor feature, which is built upon the paper on mutual information by optimizing a contrastive lower bound on mutual information. And it achieved results that's comparable to Metra. So the approach of my project is basically to look at the contrastive successor feature paper, and then by modifying the state representation learning objective and the policy optimization steps, I try to see if I can achieve a better result on the downstream task. So here are the two equations for the current methods to learn the state representation and the reward function. And basically, it's trying to align the state transition vector, the change in the states, with the latent skill vector. So one of my first idea is instead of um, doing the sampling with the latent skill vector z, I try to choose among the existing skill vector, the one that's closest to the state transition vector. And the reasoning behind this is that maybe I can try to prevent skills from overlapping that can improve the distinctiveness of the skills. The second idea that I tried is to change the parameterization when update the policy. So instead of using the current parameterization for the reward function, where I multiply the state transition with the latent skill vector, I only use the state representation of the current observation. So this way, it basically emphasizes the outcome of the agent's action rather than the transition itself. And it might be useful in environments where final state is more important than how the agent got there. And finally, the last idea that I had is to add some Gaussian noise to the state representation. And the idea behind it is that maybe it can encourage exploration by preventing the model from overfitting to the batch of data that we looked at in this equation. So here's the implementation for skill relabeling. So basically, we normalizes the transition factor and then projects it onto the closest skill vector. And then here's the implementation for changing parameterization and adding normal noise. And here are the results that I was able to achieve based on the experiments that I ran. And we evaluated the results on both unsupervised exploration and on how well it solves the downstream task. And in this case, we used the ant environment. So this graph basically shows how well the new parameterization for the reward function is doing comparing to the old method. So in the plot, the x-axis is the total environmental steps, and the y-axis is the percent of the time that the agent is within 1 meter of the goal. As we can see, the old method, which is represented in the blue line, does much better than the new method that I proposed. And this is probably because that the old method tries to maximize the mutual information between change of states and skills, and that encourages better state space coverage than only using the current observation. And here's the result of the experiment on adding random Gaussian noise. So the red line basically is adding a noise with standard deviation 0.05. The purple line is with standard deviation 0.1, and the blue line is the original method. And we can see that adding a small amount of noise actually does better than the original method. But how significant this is needs to be verified by doing a bit more experiments. And this plot basically shows the distance from the final state of the agent to the goal, and it's plot with the x-axis being the total environmental steps. And we can see that the red line and the purple line, which represent noise with a small amount of noise, tend to do better. And again, we need to run the experiments more times to see if this is statistically significant. And finally, for the experiment on relabeling, the blue line is the original method, and the orange line is the current method. The orange line is the new method that I proposed. So this basically plots the number of unique coordinates covered by the agent. So it shows how well the agent is able to explore the environment. And as we can see, our method seems to be doing a little worse than the original method. So here are some of the conclusions and takeaways for my project. So first of all, skill relabeling doesn't seem to perform as well as the current method. And but adding a small amount of Gaussian noise in the state representation update steps seems to improve the performance, but we still need to run more experiments to verify. And finally, focusing only on the final state for parameterization of the reward function does not work as well as the current method, which emphasizes on the state transition. But another idea that I had, which I will implement later, is to use a learnable weight matrix to transform the state transition before multiplying it with scale vector. And that might have the potential to work better. And that's all I have for today, and thank you for listening.